All right, so we don't have any camera image yet, but we will do the talk anyway. Before I hand it over to Bunny, I would like to start with a quick question to you. Who of you has maybe tried to repair some kind of electronics before, maybe the coffee machine or something, and struggled at the point where you saw one of these black chips, these integrated circuits, and you just couldn't figure out what it does, and that was the end of the journey? I see few hands raising, more and more. Yes, and when you think about it, not knowing what this chip doesn't only stop your progress in repairing things, but it also stops you from being able to verify that the chip does what it is intended to do. So that's actually an entry point for attackers to replace the chip and maybe drop something in that fulfills the function that it should have, and also introduce some bad malware malfunction that you wouldn't even notice. So that's probably what Bunny also had in mind when he came up with an idea how to look at the inside of the IC and see what's going on there. Big applause for Buddy.
Hello, hello, hello. It's great to be here at the Congress. It's been a long time since I've been here, since actually the pandemic that I've traveled here. I've been in my little hidey hole working on things, and this is one of the things I've been working on at the pandemic. Thanks for coming here. There are two really excellent talks also happening at the same time. I myself would not be here if I didn't have this talk, because those talks are so good. So I really appreciate everyone who showed up. I'm going to talk to you today about a technique I call IRIS, Infra-Red in situ. It's a non-destructive in-circuit verification of silicon. So it's a mouthful. Just to give you like a preview of what we're going to talk about, it's going to be some pictures like this. So chips on boards that we can actually sort of inspect and see in situ. So we haven't taken them off, didn't have to destroy them, we can use them afterwards. So just to get on the same page about what this talk is about, let's start with a problem statement. I would like to control my data. My data is in my hardware, therefore I need to trust my hardware, right? And then the question is, how can I trust my hardware? People have lots of trust issues and concerns about this thing they call the supply chain. This is like a little bit of a cartoon I made that gives you an idea of how many times your computer parts crisscross the globe on the way to do it. You may have a product designer that's located here in Germany, but then they have chip designers located elsewhere in United States or in Taiwan or wherever it is. The masks are made in another country, they're fabricated in Taiwan, they go to some IC packaging place in Korea or Philippines, and they go through lots and lots of hands, distributors, gray markets, all sorts of stuff, finally through box builds in different countries, into customs and into your place. And so there's a lot of hand-wringing about the supply side. So the politics, people are like, wow, look at all those flags, look at all those nationalities, these are other countries we don't trust, we're not politically aligned with them. Oh my God, did you say there's a gray market in the middle of all of this? Wait, this also means these jobs are not in our country, so we must subsidize this to billions of dollars to solve the problem and just, put the fabs inside of our country and problem solved, right? The problem is the distribution side is just as problematic. If you were to go ahead and build trustable, reproducible signed builds, and then you went ahead and just said, well, we're just going to have the software just downloadable on HTTP. We don't need to encrypt the connections on the back end. You'd be like, why are you even bothering to do all the other stuff when people can go ahead and hijack the connection at the end of the day to your computer? Yet we instinctively trust unauthenticated couriers. A stranger shows up at your door you've never met, hands you a box that you have ordered, and you just say, great, like this is awesome, no tampering could have happened along the way. Beyond sort of the courier problem, there's issues with like anyone as a tourist could come into your city, buy a product out of the local market, modify it, return it as a return, and perhaps someone in your city can go ahead and pick it up. So it doesn't even have to be so malicious that you have some global conspiracy to go ahead and commit supply chain fraud. It can be very targeted and local. And at the end of the day, basically, distributors are not security experts, but we're kind of expecting them to have security expertise, which isn't a good situation to be in. Fundamentally, the problem is we don't have a hash function for hardware. So hash functions are things that we use on software where we can find a single small bit change inside of a program, and it turns into a very large numerical change in some cryptographic function. Hardware is one enormous time of check versus time of use problem. So you can go ahead and check things as much as you want at the factory, but by the time it gets to your doorstep, a bit head can change. When it's in the privacy of your own home, do we have a way to as easily verify hardware as we can check hashes on a package on software? The answer is basically no today. We have a time of check versus time of use problem. If you want to go ahead and analyze a chip, there's techniques to do it. Actually, there's a wonderful talk that was just before this one, if you were here, about silicon reverse engineering, beautiful images, that sort of stuff, but it's all kind of done at very old process technology nodes, kind of 1 micron, 2 micron nodes, so very, very large transistors. On a modern chip, you have to use something like a scanning electron microscope to analyze a chip. There's a beautiful picture of a chip, but if there's something you'll notice about this chip has been cut into. This is a cross-section of a chip. After they've done this, that rest of the chip is gone, right? You're not going to use this chip that you've inspected afterwards. So you haven't inspected the chip that you're going to use. You've inspected a sample of a chip that you're now going to throw away and then buy another chip and put in its place. So it's very difficult to check and use a specific chip at these very high resolutions that you can't use direct imaging on. There are alternatives, just for completeness, things called techographic X-ray imaging, which are non-destructive. You can 3D image complex chips at nanometer resolution. The problem is that they need a light bulb that is the size of a building. So that donut-shaped structure there is the light bulb of one of these X-ray microscopes. You're not going to put one in your backyard. You're certainly not going to have every household have one of these just to check not even every large company could afford one of these. It's a pretty exotic technology, so it's mostly used for academic labs and reverse engineering. So then, back to the problem statement. I want to control my data. My data is in my hardware, and therefore I need to trust my hardware. So let's think about this more. A lot of trouble I have communicating this problem is getting on the same page about what the exact threat model is. What were we talking about when we talk about supply chain threats and silicon and so forth? So step one, let's put down some assumptions and talk about exactly what we are worried about and what we're looking for. So a key assumption for this talk at least, is that the threat is the supply chain. So the question of, is my hardware hackable, is different from the question of, is the hardware correct as delivered? So a lot of people conflate security with trustability. So someone say, I want a piece of hardware that no matter what adversary you throw at it, they can't pull the keys out or wherever it is, but then I can't look and see what it all is inside if it's constructed correctly. So you almost have to pick one of the two scenarios as your primary threat issue. If you say that I really need to have a bank vault that is impenetrable in some ways, that almost has to be delivered to you uninspectable because the inspection port itself becomes a vulnerability, right? But if you have trust issues with your vendors, then you're going to have to make some compromise and say this is the most important threat. So we're picking the trustability of the hardware as the most important threat. So whether this hardware can resist arbitrary probing is not in scope for this talk, and myself, having been on sort of the red team side of it and probed into various chips and take a look around, I'll tell you, I don't think you can win that game anyways. I haven't known of a chip yet that has resisted probing at the highest levels of any sort. So anyone who tries to sell you a chip that says this is unbreakable, you can't recover the secrets from it, I don't think you're going to win that game if you have arbitrary time with an arbitrarily powerful adversary. There are some other techniques I've been talking to people about, like essentially doing the equivalent of certificate transparency logs, but for hardware. So you can say this hardware's been on and connected to the internet and is active, and so it limits the amount of time an adversary can spend looking at it. They can use to go ahead and augment an inspectable piece of hardware to sort of confine that threat model, but this is largely out of scope for the talk. So let's unpack the supply chain threat model, and I'm going to use an analogy. I'm going to use an analogy of, can I trust this chip to, is this piece of fruit safe to eat? Because not a lot of people necessarily know about chips, but we all know about buying fruit and eating fruit. Limitations of the analogy. First of all, the stakes are different. A modified chip in the right server, a single modified chip in the right server could affect millions of people's data, right? A single poisoned fruit might make one person sick. It's not going to immediately affect millions of people. It just doesn't scale. You can poison millions of fruit, but then you're poisoning millions of fruit. The remedies are different. Chips are made in billion-dollar fabs, fruit grows on trees. So the whole answer of let's just bring the fabs into your backyard like you can plant trees also is a limitation analogy, so let's not go too far with it. However, both of these items require global supply chains, and we verify our chips just about as much as we verify our fruit before we bite into it. So, level 0 threats are threats that are very easily detectable at home or at the point of use. An example of this is a misrepresented good. So on the left-hand side here is a picture of a chip that I was duped into buying myself. This is a chip I had bought. And underneath that white rectangle were the letters ES for engineering sample. They were represented as full production chips, but someone had lasered that off and just covered it up and said, yep, this chip is good for you to buy, right? So it's a very kind of a level 0 thing. If we had looked a little more carefully, found it. The example in fruit is if you went to the vendor and there's a blemish, there's a hole where a worm would come in, and the vendor just put the price sticker right over it, right? So if you just peel the sticker back and take a look, and you're like, yep, this fruit is contaminated, I should not eat this sort of thing. Anyone can inspect it. Still, a lot of people just buy the fruit off the shelf, remove the sticker home there, and they're like, oh crap, I bought something. So still people don't even check at that level, but that's just how it is. Level 1 threats are those sort of easily detected with kind of semi-more common tools, like $1,000 to $10,000 cost level of tools. So the fruit analogy with the metaphorical like razor in the apple or pin or a piece of metal stuck in there, if you were to put it in an x-ray machine or put a metal detector on any number of easy detectors, you could find it, but still again, a lot of people never look at it. The example that I would use, the analogy of this on the hardware world would be is if I had like a network interface chip and a whole extra block was just thrown in there that can record packets and exfiltrate them, right? So there's a whole extra block on this chip. Should be easy to find. And the thing is, the interesting thing about this sort of threat is that a lot, like for example, all the IP, this is the actual data sheet image for a network interface chip. All those IP blocks you can get free open source online, or low cost to buy. You can fab it in a 65 nanometer fab. So if someone wanted to build this exact kind of attack, it would be about $300,000 up front. And you could make money selling those chips. So you could actually just make up your money if you got really popular putting these chips on the servers around the world. You could actually run a business selling modified chips. So that's like a level 1 sort of threat, whole block added. Level 2 sort of threat is sort of a one where you need kind of a more sophisticated, you're going to like a lab or a university or professional facility to look for things, $10,000 to $100,000 tools. The Apple analogy is if someone, instead of putting like a physical object in there, they've just laced it with strychnine, some kind of poison that is tasteless and odorless, and so no amount of just looking at it will help you with it. You have to go to a lab that has a gas chromatograph or a mass spec or something like this, take a sample of it, know what you're looking for, and find that particular thing. It is findable, right, but it is a little more difficult to find. The example I would use for this is like, for example, a CPU core that has been modified. Again, assumption I'm making is that there are 2 versions of the chip in the supply chain, one with the modification, one without. There's another question of, is the core actually bad by design? Like, did someone actually just maliciously design only one version of the chip and put like false instructions on the side? There are other works like this URL I leave here of people who are looking at that particular problem. This is the problem of someone's now trying to do a supply chain attack by swapping out the core. Just to ground it in specifics, and it is going to be important to sort of ground these things in specifics to understand what we're looking at. An observation you can have is that on RISC-V, the X1 register, the RA register, is the link register. Typically, compiled code only use it in very, very, very specific targets, right? In very, very specific contexts, right? You jump and link to this particular link register. And so you could use this by using that out of context to create a primitive that can potentially, for example, bypass memory protection. If you went ahead and did a load using RA as the address space, that's particularly unusual. Normally you don't load from the link register. The decoder can pretty easily pick that up and say, okay, well, instead of treating that as a virtual address, we're going to treat it as a physical address by passing all the page table protections and therefore getting past a lot of memory protections. You could incorporate stuff like secret knocks, like instruction sequences to unlock it so it's harder to discover by fuzzing, et cetera, et cetera. But the point of going into this sort of example in detail is that we're talking about something that is on the order of tens to hundreds of logic gates in size in order to implement this type of attack. So we're looking for something on that side. So it's a smaller object that is a little more difficult to detect. And finally, level 3 threats are sort of very difficult one, tailored techniques that are used to explicitly get past all the analysis. The analogy I'd have in the supply chain would be something exotic, like someone has gone and genetically modified an apple such that it expresses an antigen that's targeted to just particular people. So even if a regular person ate it, it wouldn't be bad, but then if someone with a particular genetic makeup added, it would kill them. You would have to know exactly what you're looking for. It's extremely difficult to sort of find these sorts of things. The specific example of this in the hardware supply chain would be a tailored mask edit. The example is reduced round cryptography via a small mask edit. So a lot of cryptographic ciphers consists of multiple rounds of a computational function that is done repeatedly on a piece of data. So instead of actually implementing 14 copies of a piece of hardware, they'll take the computational round and loop it back around over and over again and run that round. And so the example of how, for example, an AES computation might go on is you would have a holding register. On round 0, you'd load in the data, you would perform 14 rounds of encryption, and on the 15th round, you go ahead and hold the data for output. The observation is that if I were to go ahead and take like the bit 1 and tie it to the rest of the other bits together, so instead of allowing the bits to go up freely, you actually made the top 3 bits tied together and dependent upon only bit 1, instead of having sort of 14 independent rounds, you actually end up with only the last 4 operations that matter. If you sort of expand that out and look at what the decoding looks like, you do a load, round, round, hold, but then another load, which is, again, the data that you're trying to encrypt, round, round, hold, da-da-da. And so you've now gone from what was a 14-round cipher to a 2-round cipher at the end of the day, which is notably less secure than 14 rounds. Now, the reason why the attack is very sneaky is that if you did it symmetrically, and oftentimes the same hardware to encrypt and decrypt is oftentimes the same piece of round function that's doing it, the encryption and decryption of the data will work just fine between that cipher and its own. That faulty implementation will decrypt the encrypted data made just fine. So you won't detect it doing an encrypt-decrypt test. If you looked at this with side channels, you said, okay, what's the power signature of this thing, what's coming out? You will count the correct number of rounds. You see the correct number of glitches happening. Okay, well, what's the noise signature coming out? Well, you're actually doing computation on several of those rounds, so that will actually look really similar as well. So from a black box perspective, side channel perspective, you also couldn't pick it up. And then if you implement the chip the way you're supposed to do it, where the key is generated inside the chip and the key is completely unextractable and you don't have the key to independently verify anything, you actually have no way to know if the chip is doing a reduced round variant of your computation or not, except thorough cryptanalysis looking for a reduced round variant. You have to do that in every single chip that comes through your system. And to pull off an attack like that, again, going back to this cross section, I've pointed an arrow at that tiny, tiny little piece of metal, that little kind of copper-colored thing there. In order to do this attack, you might only need to modify 1 or 2 of those buried deep inside of the chip, and there are billions of them inside of the chip. So it's like a needle inside the haystack. It's not the sort of thing you can do without sort of delayering the chip and looking for it. And even if you're doing some of these fancy tomography techniques or whatever it is, you might even have thought that they're not 100% accurate in terms of analyzing the via there or not, and so it's within a noise margin essentially of trying to inspect one of these chips. So this is a kind of a tailored bespoke attack that is extremely hard to catch through inspection means. So the recap of the threat models. 4 levels I defined. Level 0, easy to detect with everyday tools. Level 1 is you need kind of $1,000 to $10,000 tools. Level 2, $10,000 to $100,000 tools, and level 3 requires $1 million+ tools and/or new techniques or stuff we haven't figured out yet to sort of figure out. Level 0 is kind of routinely practiced. Level 1, targeted industries might do it. Level 2 is academic papers, and level 3, as far as I know, it's destructive analysis to do it. Fact of the matter is actually to a first order, regardless of all the levels, no one checks anything as far as I know, right? A few people will open their stuff and even look at the chip label at this point in time. Most people just take the computer and say, this is a computer, it's wonderful, I'm going to use it, right? I paid all this money, it should be great, it's in a shiny case. So in general, the general public does not even check at level 0, and the public companies I do know that do checking have a policy of not disclosing problems when they find it. Because if cloud company A were to publish a report and says, we had X threats this week from APT and we caught them all, and another company says, we have no threats from APTs, we never find any of them, people will be like, well, we're going to use B because they don't have any threats, right? And so generally, when you talk to these guys who are doing these inspections, they will over beers perhaps say they might have found something, but they have very strict orders from management to never ever say, of course we have no problems at all with all the servers that are installed inside our base. We never find any problems at all. Total confidence in our data. So, to a first order, threat actors operate with broad latitude and almost no consequences in today's scenario. The work that I want to talk about today will not get us all the way to the level 3 threats, but the idea is to improve the situation. So ideally, at the point of use, at home, things that people in this room can do without exotic amounts of money and exotic amounts of time can now start to get beyond level 0 up to level 1 and level 2. So we want to reduce the detection barrier by an order of magnitude. A very important emphasis of the work is to democratize the technology, so it's not just a thing you read about in a paper and you have to have some really expensive piece of equipment, and where, you know, there's a kind of an arms race in that area right now where people keep writing all these wonderful papers, but then I say, look, I still want to just check all my chips that are coming through. And I want to improve trust in hardware for everyday people. So, the work I'm doing, it's called IRIS, Infra-Red In Situ Verification of Silicon. Is a method for inspecting certain types of chips after they are attached to a circuit board without damage to the chip. And so this one little video loop I have gives you an idea. There's a circuit board here that you can see. It starts out in normal light. I turn on an infrared light, that's the pinkish glow, and I sort of swing the light around. You can kind of see the chip glinting around. You can sort of see something's going on, and then I give you an example of like how, you know, we can zoom in and take a look onto the inside of the chip. So again, you can see this, I didn't have to remove the chip, I didn't have to decap the chip, I just had to essentially image it with the right tools. So what types of chips? The short answer is the shiny ones. If you open up a product and you see little shiny bits, those are the chips you can inspect, right? The technical terms for them are wafer level chip scale packages, WLCSPs, or flip chip BGAs. You know, they have an exposed silicon back with no film or paint applied to them. Ideally, the chips have been polished and thinned slightly. And the other sort of caveat is that the substrates are sort of P- type, lightly doped substrates. So typically TSMC or TSMC copy foundries will adopt this practice. The reason I bring it up is, for example, Intel loves really heavily doped substrates. Those scatter light a lot, and those chips are a lot more difficult to image. There are ways to get around it, but these are sort of some of the parameters. So it's like most of the chips, but not all of them. It does not work for chips that are in plastic packages. So the manufacturer, if you want to use this technique, has to be aware of it and has designed the product for inspectability by saying we're going to use this type of package. The good news, this is a very common type of package. It's almost the de facto standard in mobile phones, and so it's not hard to get chips in this package. So, seems like magic. How does it work? The principle is actually pretty simple. Silicon is transparent to infrared light. So this is a curve of the absorption of silicon versus wavelength of light. And so here on the left-hand side is visible light, and we can see that light only gets some microns into the chip, which is why they look shiny and stuff reflects off. And then this particular band I showed of interest that's highlighted in tan is our target wavelength of around 1,000 to 1050 nanometers, and the light will actually get 0.1 to a millimeter depth into silicon, which is about the thickness of a chip. So right around there, silicon starts to become quite transparent. And the second factor that makes this really interesting is that standard off-the-shelf CMOS sensors. So this is not exotic gallium nitride or gallium arsenide sensors or whatever it is that you were talking about. Just standard CMOS sensors actually have sensitivity into that band. And there are some camera models out there that are explicitly tuned to take advantage of. These are the ones for the surveillance market. So cameras that you put on surveillance that want to look at, for example, night and have enhanced night vision, they'll have a filter characteristic like this, where you can see they've plotted, this is the Sony Starvis 2 line. There is a blue filter that's enhanced in the blue domain, the green filter that's enhanced in the green domain, and red. And then once they get beyond to the infrared, they actually sort of become fully transparent, and around sort of 850 nanometers, you have really great sensitivity, and it starts to drop off as you start to get into the, near the band gap of silicon and the inability to actually capture those photons. And from the datasheet itself, they have an example, for example, on the right-hand side is what that sensor looks like with that enhanced infrared sensitivity. You can see that it in the dark, essentially, it functions as a night vision camera, as it may be. And so these are inexpensive CMOS cameras. They're not super exotic. Take all that stuff and you put it together, and you have effectively what Iris is. So this is a summary of the technique. You have a chip. It's already mounted on the circuit board as a product. So it's been delivered to your home. You don't have to take it off. You don't have to decap it. You don't have to do anything. You just have to take the plastic case off, shine a light on it. The light will go ahead and reflect off the metal inside of the chip, come up and go into the camera, and you can capture it. This happens in situ after the product has been assembled. So just a little note on prior work. This is not a technique that is completely new and like I invented everything from scratch. Actually, I had seen the first hint of this inside a paper in CHES 2018 that was referred to me by Dmitry Nedespetov. Key extraction using thermal laser simulation, and this is cool. They had this like image in here of a chip that was an image from the backside of an FPGA using a laser scanner on $1 million machine. I was like, wow, this is super cool, but it's $1 million machine. I can't afford it, but I would love to be able to do that sort of thing. And then I came across a Flickr feed of a guy named Christian Fritz who essentially just does this as a hobby. And I saw this sort of like little sort of hint picture of it that he had when someone was asking how I was doing it, and then I sort of put one and one together. I was like, oh, this actually could be a really good technique for just checking chips, and like how far can we take it, right? So then some questions like, why do we insist on looking at the back side of the chip versus the front side of the chip? When I say back side and front side, this is a cross section of a chip. It's a huge stack of different things. The back side is on the bottom here of this slide. And that is what's near the transistors on the bottom. As you go up the metal layers up the top, you finally encounter the balls that are on the package, right? If you were to look at the chip on the front side, this image here in the top middle, a lot of the chip is obscured by the solder balls or by large pieces of metal. So there's lots of places where you can hide exploits if you were to check it from the front side. If you check it from the back side, however, you are looking directly at the transistors, right? So you can actually get a sense of the transistors on the chip. And so this image here that I have, maybe a little bit easier for me to point over here, this is pointing into this square here that you can see. And that square is literally a transistor. That is what a transistor looks like in a modern process. It's an analog transistor. It's part of a sort of an op amp or something like this. But you can now actually see transistors on the chip with this particular technique. So what do the implementations look like? Well, they can vary in terms of price. At the low end, for a couple $100, depending on your tastes and how much you want to buy stuff of AliExpress or versus like name brand vendors or whatever it is, you can dial the price. For about €300, you can just do it at home. And I brought a setup over here to use as a demo after the talk, but we're having a little trouble getting it to connect to the camera, so we'll see if you can see what it looks like. And then at sort of the higher end, you can actually put it into a CNC machine and do like step and repeat imaging of chips to generate very high resolution reference images. So the version with manual adjustments, you can see here, and actually this is almost the demo that I'm going to show you, so if it doesn't work out, you can kind of see what it looks like. You can see on my hand here, I'm just swinging the light back and forth in the lower left hand of the frame, and you can see there's a chip there with the Apple logo on it, and you can see glints of the transistors there underneath the inside. The silicon, because it's transparent to infrared light, basically looks like glass with that imaging. And this is what I'm using here is a regular Sony camera that has the infrared cut filter removed. They all ship with a filter to remove the infrared because normally it's considered an artifact that contaminates artistic photos or whatever it is. But if you're doing engineering work like this, you really want to have that filter in place. And so you can go ahead and modify cameras and do that. For automated adjustments, I built a platform that has actually a fully CNC controllable light source and directions and whatnot. So this is a thing that I sort of put together in my home workshop. It has 10 micron repeatability in terms of XYZ positioning. I can position light in multiple dimensions around it, and it's useful for generating reference images. So other people who want to, for example, say, is my chip correct or not? You want a really high resolution sort of map of a chip, we can use this to extract those so other people with cheaper setups can sort of do a comparison against that. If you have an application where you need to do very high throughput screening or you need higher confidence measurements, you may be interested in investing in something like this as well. So the actual platform itself, the motion platform is I didn't build the CNC part. This is a platform called Jubilee, developed by Professor Nadia Peek's laboratory. It's open source. It's a 3D motion platform with a kinematically coupled Z-stage. You can go to this QR code over here and read all about it. So the actual chassis itself is like an off-the-shelf piece that you can basically pick up and play around with yourself. The part that I did make is the microscope core. So this here is essentially what you think of as those microscopes you see like in the science lab. It's just, I thought they were like crazy hard things to build. I'd never done these things before. They're actually just basically two lenses. It's called a tube lens and the objective, and they stick them together, and then you put the camera on top. That's it. That's all a microscope is, with a bit of geometry to put the pieces together. So the microscope itself is actually pretty inexpensive and easy to build if you build it from parts. The hard part was more the light sensors, so the lighting itself. So the lights, the LEDs, are mounted on PCBs in the bottom. They can shine in, and I can sort of adjust them independently to shine at different angles onto the chip, and I can also rotate them around on an axis compared to the chip. And the reason why I went through all this effort is, if this video plays, this is what happens when you take the light and you shine the chip, and I'm rotating it around the axis. So you're seeing the light just sort of rotate around, and you're seeing that each of these different diffraction patterns are happening. So if you've ever seen a hologram, like how does this flat thing give me a 3D image as I rotate it across? Essentially what a chip is, it's a big diffraction pattern. And depending upon the angle of incident light, you see different things. So one of the first objections the astute observer will have is like, well, you're imaging sub-nanometer features with photons, which are very large. That is true. However, the diffraction of that photon playing around with a chip gives more information than a single still image. So one of the reasons I built this is to try and extract that extra information so we can do some computational work to try and figure out what the composition chip is based upon the diffraction pattern, the angle of light, and so forth. Another piece that I built is a nanometer fine focus stage, which actually turns out you can build them for under a couple $100. If you were to buy these just full up, they'd be about an order of magnitude more expensive. All it takes is 3 piezo actuators. These are the ones from the automotive industry where if you like use a touchscreen, it sort of has like these little bumpy buttons. It feels like it's bumping back at you. They're already in volume in cars. You put 3 of them, and you put them on what's called a kinematically coupled stage, right? And this is one of those things that's like super beautiful, and it's like one of those nice just so stories when math lines up with physics, lines up with mechanical stuff. If you were to model the motions, the equations of space, it takes 6 points to uniquely define where an object is. So 6 points in space. How do you create a point? Well, it's a tangent of a circle and a line. How do you build that in real hardware? You take a glass bead. This is actually a glass crafting bead, like the types you use to like put raindrops on like the wall in Graph Project. You can buy them for like a penny. Take a glass bead and you put it on a V-shaped groove. And that creates 2 points of contact. And because glass is very hard and aluminum is very hard, that point of contact is very, very, very tiny, essentially a point. You make 3 grooves like this, you have 6 points of contact, and you have a stage where you can take the thing off, look at it, put it back down, and it will set back exactly where it was before, down to like sort of nanometer scale precision. And so you now have what's called a kinematically coupled stage for essentially the price of glass crafting beads and some milled aluminum. So a few little tricks like this kind of work through to try and figure out how to make the technology a little more accessible, a little cheaper, so that everyone can play with it. In addition to all the hardware, there's a ton of software that has to be written. And as a hardware guy, this has sort of been like the slow thing I've had to accept over the years, is that I get to have fun building hardware about 10% of the time, and 90% of my time is actually writing software for it. It's really all in the software these days. So I had to write a ton of software that can go ahead and do the step and repeat. It does the autofocus, so essentially I do sort of a focusness metric, figure out where the peak of the focus is after I sweep the Z stage up and down, and then take a picture, move over a section, and then take that, and then we end up with a bunch of tiles that ends up representing the full chip. The focus convergence is pretty good. Gets better to less than 5 micron on average, which is within the depth of field limit for the objective. 10 seconds per image step. And then there's some problems if you have top markings on the chip that can interfere with it, but you can algorithmically get around with it by sort of interpolating where the chip is on a plane. After you've gone ahead and imaged a large chip, for example, like this MediaTek chip over here, you can see you get a bunch of tiles that aren't perfectly aligned. The reason why they're not aligned is just because of natural mechanical tolerances of the system. You could buy better motors, but you can also just compute your way around it. So again, instead of tinkering with hardware and getting the slack out of the motors, I spent a lot of time writing software. And I wrote a sort of program that does template stitching and MSC cleanup, minimum squared error cleanup. I can stitch about 200 images in, is the animation running? Yeah, I can stitch about 200 images in about 10 to 15 minutes. And have a little UI for doing the real work, to rework and all that sort of stuff. If you're interested in anything of the stuff that I've talked about, you can go to this URL here, scan the QR code, bunny.org/iris. And I have blog posts on every single one of these things. I have links to all the source code, links to all the hardware documentation, blah, 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 all that sort of stuff. You can knock yourself out and read all about all these particular subtopics. So, thank you. Thanks. That means a lot. Some examples, you can go to the Silicon Prong website. There's a QR code. I uploaded a few very large chip images there, so you can go ahead and take a look at them and browse around them. More specifically, let's kind of look at what we're looking at here. So this is a Sky 130 process, 130 nanometers, right? You have a bunch of these little bright blobs, or whatever it is. If you actually take the design data and you overlap it, you can see that the brightness of the blobs correlates to the rough gate type. So as a logic gate, a flip-flop, NOR NAND, buffer inverter, you can see some correlations of that type, and 130 nanometers. So it turns out that like 130 nanometers, a gate is about 30 pixels on a side or something like this, right? I also happen to have a 22 nanometer chip that I have the design source for. And we can line those up, and this is at the same pixel size, so you can see the gates are much, much smaller, and those logic gates are about 3 pixels on the side, or wherever it is. So it gives you an idea of between like 130 and 22 nanometers, all the technology nodes in between, you can get an idea of how well we can see gates and what we can detect and what we can't detect at the end of the day. So now that we have an idea of what we're looking at, what does it get us? Let's review our threat models. Level 1. Block level modifications. You know, if I have a chip in a wafer level chip scale package, it is relatively easy to diff out modifications. We would need reference images, of course, but you can just sort of eyeball them. So hypothetical Trojan I've been talking about, let's just say we put another block in there, records a few kilobytes of network traffic. If it receives a magic icon packet with some key in it, it'll go ahead and exfiltrate it to some server, some command and control center, whatever it is. So like little device like that. On a real piece of silicon, if this were to implement, I'm not saying this one has it, but just to give you an idea of how big these things are, this is a 65 nanometer node piece of silicon that I imaged. This is about 4 millimeters on one side, and you can see a small CPU core is the size of that dashed area there, and that little darker rectangle there on the side is about 8 kilobytes of RAM, and that's just figured out by just counting the lines and going through stuff and whatever it is. And so if you were to have a block level modification, you would see an extra one of these sorts of things on it. It would just jump out right at you. It'd be pretty easy to find. Level 2 modifications. Again, if you recall, that was the talk about the section I was talking about, like a CPU core that has been modified with some sort of like instruction that has been tampered with or whatever it is. Like I said, about order of 10 to 100 logic gates. What does that look like on a piece of silicon? So if we're to go ahead and look at this, this is the place and route logic pattern. So if you to sort of look at this chip, you see here there's these modeled blobs, right? It turns out when they run place and route, the logic tends to cluster together. You have a flip-flop and you want to put the logic around it, so it kind of creates actually a circle around it because like speed of light, timing, whatever it is, it all wants to be in a certain radius of it. So you have these blobs that essentially correspond to different logical subfunctions. Each one of those blobs is theoretically about 100 gates. In practice, it holds much less because your routing density limit rather than gate limited. So that sort of modification would cause an extra one of those blobs to appear inside of the chip, right? Something like this, or change the shape and size. Now, astute observer would note that logic gates only show up as fuzzy blobs, right? So we can only kind of say what type of gate we're talking. In reality, we can only know how many gates are in the region. We don't know exactly what types of gates are there. So a very clever adversary could say, okay, well, let's lock down the place and route and just swap out different gates without changing the total gate count or something like this. Hypothetically, that can be done, but it would definitely leave a trace, some sort of detectable trace, because you're going to have reduced timing margin or power consumption changes, because those place and route engines put the gates there for a particular reason. So if you're trying to constrain something and push more gates in the area, there might be other ways to sort of detect the situation. A related work in progress is I'm also just trying to figure out how to automate the gate count census. So I have some chips where I have the design source, I have imaging data, and I have now some automated algorithms that can go ahead and align up the rectangles that correspond to the cells, to the light and dark blobs in the chip. And then since we are in 2024, of course, we want to throw it into some ML kind of blah blah thing that I really am out of my depth trying to do anything with. But you can read some papers and play around with it. If anyone here is good at this stuff, I would love to hear some advice on how to do this right. But the idea is to try and train something to look at these samples, of which we have tens to hundreds of thousands of gates to look at, so we can train it pretty well, and come up with sort of a gate count G plus minus some sigma, right? So the uncertainty, and this is always inevitable in any physical measurement, at the end, Heisenberg will win, right? There's also more practical things, just like noise, dirt, scratches, process variations, whatever it is, blah, blah, at the end of the day. But we can at least constrain the number of logic gates that are on a chip with some analysis like this. And it's a bonus if you can classify the logic cell types. Now, you say, what about level 3? We talked about that. Well, by design, that particular attack was meant to defeat this, right? It was a small change on an inner metal layer. You're not going to detect it with this particular thing. And actually, honestly, I don't think we have any good answers for how we practically detect these at scale, right? We have lab analysis, and we have papers on things on how you can do it. But if you're just going to say, we have reason to believe that an adversary is tampering with our AES units and give us reduced round variance, but we can't get to the keys to verify anything, how do we know? Help, help, help. It's an expensive problem to try and solve right now, unless you have something, for example, like scan chains that you allow on your chip. But of course, this means you now have scan chains on your chip, which is a different, problem to talk about. But basically, the hypothetical next step that you would take this if you want to get to 100% confidence is that you start with the observation that Iris is very good at qualitative analysis. So how many memory blocks do I have? How many analog blocks do I have? Where are the I/O pads? How big are my logic regions? It can be somewhat quantitative in that it can give you the rough bits of memory, how many standard cells we have, that sort of stuff, but it's not good at functional stuff. I can't say you have exactly this equation in Verilog or whatever it is. Scan chains are great at the functional stuff. That's literally what they're for. In fact, the smaller the logic you're looking at, the more precise you can be with a scan chain. But because scan chains are putting bit patterns, bit vectors through, and essentially looking at Boolean vectors, the complexity grows exponentially. So as you get to the chip level, you can only effectively explore a small portion of the chip state, and so it's bad at capturing the full chip level stuff. If we can sort of merge those two techniques together, we might be able to get full functional verification of the chip. And there's a whole bunch of stuff that, for the future work I want to talk about, we don't have enough time to get into, so I'm going to wrap this up. Even if we can't get to 100% confidence, I would argue that Iris is better than just trusting the label. If you read the label on the chip, you get about 64 bytes of text that you're just sort of verifying against the database. If you have a chip that you image at this level, you have a 100 megabyte image, roughly, that you have generated. So between those two, there's orders of magnitude of data. You can probably do some analysis to catch something, I would say. And again, the status quo today is that basically, to a first order, nobody is checking anything. A few people are checking at the simple level, but basically the threat actors at this point in time operate in a zero risk, zero consequence scenario. again, behind Iris, the idea is that there are some things we still can't catch, but Iris could raise the bar. So those things that were previously out of reach, sort of level 1 and level 2, I would say we can get it bound just into the level 2 threats. Definitely we can catch the level 1 threats, and the level 0 threats are easy to catch. So part of the reason I felt it was important to share this talk here at places like the Congress is that even a modest adoption of Iris may work as a deterrent to threat actors, right? Right now, the threat actors operate in a no-risk situation. So even level 0, level 1, level 2 threats, they might be even incentivized to do those. Why not, right? They're low cost, they're easy, they're high reward types of things. So, but if it became known that we're members in the community who are just regularly doing this, even as a hobby, they would now have to suffer the possibility of even being caught, right? And that can be enough of a deterrent to go ahead and actually immunize a larger portion of the public from these types of threats. And then, of course, ideally, products are designed to facilitate this kind of inspection. Like, products as they are today are not 100% inspectable by this. You have to choose the right kind of chip. You have to sort of facilitate. You have to publish some amount of reference material to compare against. This only happens if there is demand for this. So by creating awareness of the potential of the technique, if you think it's important, we can start having conversations with product designers to see will they be willing to go ahead and make products that incorporate these features to facilitate inspection, and particularly for security critical things. And the other thing, finally, is it's just fun to look inside of chips, right? Let's be honest. One of the big reasons that I did this, particularly over pandemic, I just like looking inside of chips. I just looking to see what's inside of it and enjoy it. And so a lot of it was just the joy of inspecting them. And if it's possible, I don't know if they managed to figure out the demo issue, I would like to share that with you. If not, we'll just pop over to a Q&A. I want to first say a big thanks to NLNet for an NJ Zero and Trust grant, which allowed me to do this, and also to my GitHub sponsors who sponsor this effort. And because of this, I didn't have to seek any funding, no VC, no sort of like ties, conflicts of interests. I can actually make this work free, open source, everyone to use, no patents or nothing tying me down on it, which I really, really appreciate. So thank you everyone who sponsored me to do this effort. Again, you can go to bunny.org/iris to find more. And then tomorrow, particularly if the demo doesn't work, near the fail overflow assembly, which is sort of in the H3 foyer area, we'll have a pointer to the microscope nerds meetup, and we can actually go ahead and look at that setup, and you can look at some chips with me, and we can sort of see how this works in real time if you want to see, particularly if I don't know if they're able to figure out the demo thing and bring it. I think we were unable to get the camera to sync up to we had even problems getting the laptop to sync up to the projector, so I think there's no hope of the cable getting all the way back there. If they had a handheld camera that could point it at the screen, we may be able to show people, but it looks like the handheld camera didn't show up in time for us to do that, so maybe we just cut the Q&A and I can maybe pull up some images on my laptop and show people stuff.
Thank you, Bunny, for this wonderful talk. So you definitely made me curious about hardware security on a whole new level. And who's also curious, I would imagine, is our audience. So if there are any questions, please line up behind the microphones. If there are questions from the internet, go ahead and ask. I already see two people wanting to ask something on microphone number 3.
Hi, first, thank you for your talk. You mentioned brilliance of the light sources. In your experience, how does brilliance of the infrared affect resolution?
How much does the brilliance and the intensity of the LED affect the resolution? You need the actual trade-off is two trade-offs. You can make up for a lack of intensity with time. You can just open the shutter of the camera for longer, but that means you have more sampling noise, particularly due to vibration. Like these things, like I now know when the metro system stops running in Singapore because like I can only do measurements after midnight in my place because the metros keep running and they shake the microscope, right? That's how sensitive the measurement is. The other thing it affects is noise. So more light means you have less ambient noise integrating into it, so you have a higher noise threshold on it. So those are the two things. on the particular device I had, this is one of the fun things I did. The 10, 15 nanometer LEDs, if you go to DigiKey or something like this, they would want to charge you 10 euros for one of them, right? Something about that price. Super expensive. Turns out, if you know the right people in China, you can get them made for about 10 cents a piece, right? And so I found some guy, and I had to order real of them, so like I had to pay $300 for 3,000 of them, or whatever it is. But it was much cheaper than buying these $10 LEDs one at a time and putting them on. So I just had a custom reel of LEDs made, and I used 5 of them on each of those individual things. So I have 500 milliwatts total intensity going onto the platform. So that helped a lot.
Nice, thank you.
Yep.
Next up, there's a question from the internet presented to you by our signal angel.
Okay.
Mastodon wants to know, would it be possible to actually use iris on plastic packages by decapping, but from the bottom up to access the die?
Yes, as long as you have the backside of the die, you can image it with the caveat that the backside is smooth. Particularly on the older chips, they did a rough cut on the backside of the chip, and so you have a lot of grooves on it, which will interfere with the imaging. But I don't know the exact reason for why this is the case, but most of the modern chips have very highly polished backsides, and I think it may be just they want them to sit really well in the chuck, so when they do the imaging and the masking and photolithography, so those things are polished, like mirror smooth. They just come out perfect for imaging on the more modern chips. But if it's an older chip in the plastic package, it may be you may have like a rough cut back silicon side. So.
All right, microphone number 1, please.
Yeah, basic question. How did you cope with laser engraving and lettering by color?
Okay, so if there's laser engraving on the back of the chip or something like this, right?
Or on the front, yeah. Well, from the top perspective, yeah.
Yeah. I mean, so you can see some of the images, like this guy here. There's laser engraving, right? And so underneath where that big M logo is, you can't see what's going on. It's just obscured by it. So again, this is where the manufacturer needs to cooperate a bit and use the right type of laser marking. There are chips that are fabricated with laser markings that they're marked, but they actually don't interfere at all. Like, so this chip here has marking on it, but you can actually do a style of marking where instead of actually ablating the silicon to do the marking, you simply change the color of the silicon. They're a little harder to read. If you shine them in the light, you have to almost look at the right angle to read them. But when you do that, you don't see the marking at all when you do iris imaging on it. So again, if you can design chips essentially to be inspectable with this technique and still have the marking on it.
Thank you.
Yep.
Mic number 4.
Hi, thanks for the talk. Also the question I want to ask is this: how do I know what I'm looking at, right? So if you have, let's say, I have a product and I see this chip with this part number. How do I know what? Because you said that this is more for okay, maybe you're talking about someone who knows some degree of electronics, so maybe not microfabrication. So how do you know what process nodes are being used? That sort of thing. And even if you do detect, I spot something.
Right.
What do you do about it?
Yeah, exactly. So again, when I was laying out the threat scenarios, for example, I was talking about the one where someone has modified the CPU pipeline. The assumption is that you have 2 types of chips in the supply chain, one that has not been modified, one that has been modified. So in the typical case that we're talking about the supply chain threat scenario, we're talking about an image diff. Right? You actually don't even need to know what's going on inside the chip. You just know that there was a significant difference between the 2, as long as they're reference images. If manufacturers publish a reference image of what it should look like, then it's even better. Of course, they don't do that today. But beyond that, if you wanted to actually, like I do, I want to have fun and look inside the chips. It turns out actually there's a lot of common primitives on the chip, and I actually got some samples from another team located here in Europe, and they actually had chips fabricated in 22, 45, 65, 90, blah, blah, that sort of thing. I'm imaging each of them. Essentially, you can create a register of primitives that gives you an idea of a gauge, essentially a gauge to say, this is the node of fabrication because this is how big the gates are, this is how big things are. So you can now take a look at it and say, okay, this chip is roughly in this node. The RAM macros all have a particular type and style to it. There's a bunch of patterns you start to recognize. So if you also wanted to get into more like the reverse engineering angle there's that as well. But from the pure supply chain status, we don't necessarily care what the functions are. We want to know if they're different A versus B. But this is not going to find like someone who's crafted a single version of the chip with malicious logic, and that's a different, I consider out of the scope of this particular problem.
Thank you.
Yep.
There are more questions on microphone number 3. Go ahead, please.
Hey, Bunny. This is really exciting work. Thanks a lot.
Yep.
One threat that I had in mind when you mentioned that there's a gray market, I guess somewhere between 0 and 1, is that the threat of some OEM buying a fake part that looks like the real part, putting in the product, and then you find it at the end customer, but, well, it's the fake part in there, and now you have a problem.
Right.
Do you think that it would be possible to implement Iris at scale at an OEM to verify the entire supply that comes
Absolutely.
in?
Yeah, absolutely. This is a thing that we could actually build. You know, when you have like an SMT line, they have like the conveyors and parts. You can just put as a module inside the line and have 100% inspection of the chips as part of it to catch. That's the sort of thing that we can talk about. They aren't the focus of this particular work, because I feel like those guys would solve the problem if there was demand to solve the problem right now. Like maybe if a particular customer says you have to do 100% inspection. And actually, I kind of also noticed that Apple chips tend to be very iris imageable. I wonder if they don't just do that already as part of their supply chain. It's possible. I don't know, right? But you know, just so happens most of their chips image really well with this technique. And so I think that part may be more solvable. A lot of the concern of the work is to democratize verification, because what we really want is we want everyday people checking. We want people to be able to watch the watchers and make sure that things are going on, create that kind of pushback threat against the APTs to say, like, look, you could be caught. Maybe you should stop, you know, feeling that you have the playpen entirely to yourself.
Thank you so much.
Yep.
Number 4, please.
Hey, thanks. That was an awesome talk. I really like the taxonomy, the threat taxonomy you had, and the budgets aligned with it. What would you think would take to covertly operate any of those? Which is to say, at what point is it obvious you're running a program such as that if you're, you know, wearing the threat actor hat?
Like I said, for example, the level 1 threats, I contemplated building a NIC myself with open source parts and throwing it into like one of these kind of tiny tape out programs or wherever it is. I'm like, okay, it's not inconceivable that like it's not a big budget to do those. Level 2 sorts of stuff, like there's suspicions that it happens already, but we don't know. It's not a huge amount of budget. Level 3, where the tailored edits are happening, that's really, I think it's less that it would leave a mark. It's more like how much access do these guys have to the fab, and how much, like, for example, is a manufacturer colluding with an APT. So like if someone says, well, you just asked for $5 billion in grants, it would be really handy if you let Colonel so-and-so here into your fab and just have a look around in exchange for $5 billion or something like this. And then, you know, he looks around and says, you know, let's put a couple VIAs on some special SKUs over here destined for that country. How would you feel about that in exchange for the funding? Or there might be some troubles in politics, you know, that kind of thing. So, you know, these are the types of scenarios that might be out there that would keep me up at night.
And if I could follow up, if you had to look one of 2 places first, would you look at academic contracts or defense contracts to try and, you know, shed some light on that?
Oh, who's working on this types of stuff? It'd be, I don't think the academics would be pulled into doing this. It would be more pragmatic, even at corporate level. But also there's like a recorded case where apparently NXP had like threat actors running through their chip network, like the chip design database for 2 years undetected or something like this. And then they're like, oh geez, like someone had access to all of the chip designs and everything for 2 years and we didn't even notice, right? So that would be the sort of thing I'm like, well, you know, what's going on now with those chips and what's happening in that area? That would be the sort of thing that would be a potential vector, right?
Thanks.
Yeah.
All right, I know there are still some open questions, but we are tight on schedule, so I have to close the Q&A now. Contact information is on the slides if you want to reach Bunny afterwards.
Yep.
Otherwise, there's nothing left for me other than saying thank you for your wonderful talk, and please give another big round of applause for Bunny.
Thanks everyone for coming.